Standard language models operate on probability. Financial and compliance audits require mathematical certainty. Because of this gap, the prevailing consensus in the industry is that artificial intelligence is unfit for formal accounting functions. This diagram illustrates exactly why standard AI fails compliance audits. On the left, a standard model produces probabilistic, unstructured text without maintaining a persistent state across interactions. Its reasoning is entirely enclosed within a black box log. On the right, a formal audit process demands a rigid state machine, where discrete, verifiable inputs are processed into tightly constrained, repeatable outputs. We cannot fix a probabilistic engine by adding more instructions to its prompt. Prompt engineering is simply a linguistic layer attempting to regulate a statistical core. To achieve actual control, the system must be rebuilt around structural enforcement. To deploy artificial intelligence in a regulated audit environment, the probabilistic text engine itself must be converted into a strictly deterministic state machine. The architectural blueprint designed to execute this conversion is called Phoenix Daemon. Phoenix achieves this conversion through three distinct pillars. First, strict structural determinism. Second, cryptographic audit trails. And third, absolute data sovereignty. When an AI is treated as a highly constrained orchestration substrate rather than an open-ended chatbot, it becomes possible to build compliance workflows that satisfy the specific documentation and transparency requirements of financial law. Setting a language model's temperature parameter to 0 produces predictable text, but it does not produce structural determinism. Determinism requires hard architectural constraints on what the system is allowed to execute. Here is the 16-stage pipeline manifest that drives Phoenix. In this layout, the language model is merely one tightly regulated component within a mechanical sequence. We need to look specifically at the transitions between Pass 1, ground, and Pass 2. In the Pass 1 stage, the system receives the initial context, deliberates, and drafts an initial conclusion. During this deliberation, Pass 1 is structurally forced to explicitly cite specific load-bearing memory IDs. If the model wants to make a claim, it must output the exact identification tag for the historical ledger entry or policy decision that supports it. That packet then hits the ground stage. This is a safety-critical mechanical verification barrier. Ground takes the cited IDs and queries the database to retrieve the exact source text of those specific memories. If a cited memory ID does not perfectly resolve, the system fails closed. The ground gate physically blocks the data packet and the action is halted. If the verification passes, the rehydrated ground truth is passed to Pass 2. This stage uses only the verified facts from the database to regenerate the final executable actions. Even when actions are fully grounded, they pass through a final gateway. Every proposed action is classified into a 4-tier system. Irreversible Tier 3 actions are halted entirely until a human operator issues a single-use approval token. Standard AI agents routinely execute code based on justifications they invent on the spot. This multi-pass pipeline separates the drafting of a plan from the verification of its premises. By structurally forcing the AI to successfully pull verifiable database records before it is allowed to act, the operational risks of AI hallucination are neutralized. An automated financial decision is legally worthless if the logs recording it can be silently altered or deleted after the fact. Phoenix uses a dual-write logging architecture. Every event, block, and approval is written simultaneously to a local JSON-L file and a Postgres audit trail table. Look at this database architecture. The audit table is protected by row-level security. When the application role attempts to execute update or delete commands on the audit record, the database structurally rejects them. Because the application role physically lacks the permissions to modify historical rows, tamper resistance is enforced by the database engine itself, regardless of what the application code is instructed to do. The JSON-L log file serves as the definitive backup, secured by a mathematical foundation, an HMAC SHA-256 hash chain. Every single log entry contains 2 cryptographic fields, a previous hash and an entry hash. The entry hash is generated using an offline operator signature. It then becomes the previous hash for the row immediately below it, creating an interlocking relationship down the entire file. Altering a single digit of historical data within any row invalidates that specific entry hash, immediately severing its connection to the subsequent row. This breakage cascades all the way down the chain. It eventually hits the audit chain checkpoint table, which records the last known valid state of the log. When the verifier script parses the file, it reads this entire sequence. It can explicitly identify exactly which lines suffered an in-place edit and cross-reference the checkpoint to detect if entire files were quietly deleted. This cryptographic continuity provides external compliance officers with mathematical proof that the AI's operational history is intact, unmodified, and admissible. Regulatory frameworks like DORA and GDPR carry strict mandates prohibiting the transmission of sensitive financial data to third-party cloud processing centers. Phoenix is expressly designed to deploy entirely on local, on-premise infrastructure or within heavily restricted air-gapped network environments. Processing data locally guarantees data sovereignty. It physically prevents sensitive audit materials and personally identifiable information from leaking out to external SaaS providers. Running an AI platform across an enterprise also requires severance, the architectural isolation of different AI personas, such as DevOps and compliance, operating on the exact same engine. Postgres row-level security executes this severance. By automatically appending strict namespace filters to every database query, the system physically blocks a DevOps persona from reading or interacting with data that resides within the compliance persona's namespace. This isolation prevents the operational hazard of scope creep, where an AI is manipulated into discussing or executing tasks outside of its authorized domain. To defend against scope creep before it starts, Phoenix uses a fail-closed domain gate functioning as a pre-pipeline firewall at Layer 1. If a prompt is out of scope for the specific persona, it is structurally rejected at Layer 1. The input never reaches the language model, neutralizing prompt injection attempts before compute is even spent. True regulatory compliance cannot be built on fragile prompt engineering. It requires physical network isolation and hard database-level severance. The probabilistic nature of standard language models makes them inherently incompatible with the rigid demands of accounting standards. Database-level severance and strictly on-premise execution solve the regulatory requirements for absolute data sovereignty. The grounded two-pass pipeline solves the critical liability of hallucinations and unverified actions. And the dual-write HMACA SHA-256 logging system solves the demand for tamper-evident, auditor-grade transparency. By enforcing determinism through rigid architecture rather than linguistic prompts, the primary barrier to using artificial intelligence in formal auditing has been removed. Enterprise organizations can now scale their compliance operations autonomously, matching the speed of modern threats while exceeding the rigorous standards required by global regulators.